Welcome. This is Tom Kaler, and this is a talk about sort of the culmination of many decades of work in trying to understand uh, if we can come up with a sort of fundamental understanding of how groups think. How do we co-create? How do we uh, discover new ideas together? Uh, all of the progress in humanity and human society has largely been a result of collective intelligence. And so this talk is about a field theory of collective intelligence. And uh, that's what we're going to cover. And so this is actually an entire framework for that. So let's get on with it here. The first thing I want to say is that fundamentally, what we now understand as deep learning and AI really comes from uh, an understanding of the natural laws associated with cooperative phenomena. This is something that emerges out of magnetism. The video to the right is a device constructed at MIT that simply shows a group of magnets that are connected, but they interact with each other in the same way that when you have birds flying, they have nearest neighbor interactions that propagate in waves in different ways of orchestrating that behavior. It appears chaotic, but underneath it is an emergent patterning that happens. And this talk is about understanding those patterns and then understanding how that impacts the way we work and think together. Now, it turns out that all of the stuff that you see today in large language models comes out of deep learning. And you see here in the lower left, Jeffrey Hinton giving a lecture. And guess what? He is showing the Hopfield model. That energy expression is energy of interaction. And it literally is a copy. And what Hopfield showed and got the Nobel Prize for it in 2024 was Nobel Prize in physics, that is. He was able to show that there is an isomorphic relationship between how the brain works in memory with and memory constructions and patterns with how uh, the theory of magnetism works, and that is his fundamental discovery. And then the Hopfield neuron, artificial neuron, underpins deep learning. And that was taken further by Lin, Tegmark, and Rolnick in a paper about 7 years ago out of MIT, which really showed that you can reduce all of deep learning to a physics description using a Hamiltonian. And that's what this talk is about. Is we are at a moment where generative AI is being promoted as the right long-term path. And that's where you're simply learning from data. What this talk is about is there's so much more, maybe orders of magnitude more that you can learn from the interaction of intelligent beings, human beings, interacting with each other. But furthermore, this same framework allows us to bring in AI agents, so it isn't disruptive to progress. This is just saying that a generative collective intelligence becomes a turbocharged booster to what we've gained so far with generative AI. So do not read this talk as proposing something that's tangential to what we've learned so far from these linguistic models. We can actually now take it to a new stage, which I believe is going to be the real stage of super creative outcomes, simply because the human brain has 100 times to 1,000 times the power of even the best of the current large language models. That isn't being propagated so much in the news today. But the fact is there. We have something like 100 times the number of synapses as points of connection within the largest models or the number of tokens, et cetera. We're talking trillions. And we also have learning patterns that have gone over the entire history of life. And that evolution has cumulative learning embedded in it. This is why salmon know how to find their point of spawning. I mean, all of these things operate within nature. And that's what this talk is about, is to return to a deeper scientific look. And it has immediate application to building trusted and trustworthy use of AI in solving our biggest and most challenging both corporate problems in innovation and transformation and social problems in things like deliberative democracy and citizen assemblies. So in this talk, we lay the groundwork for a field theory of collective intelligence as a basis for a new kind of operating system. By the way, one that we've been experimenting with for at least the last decade, that orchestrates, synthesizes, and records collaborative creativity. So let's now step back. What does a group actually believe, and how does that belief change over time? This is fundamental to the scientific process. What works? What do we go back to Copernicus? Copernicus said this is a model of the universe. The Earth is not the center. Galileo uh, did some experiments which prove that. But over time, this became the dominant understanding that the Earth is not the center of the universe. The universe is very large. That's a collective intelligence process that went from it propagated over time. And that's what we want to look at. And that whole process of how ideas, think of the the structure of scientific revolutions is based on this idea of emergent learning that comes from group deliberation and collaboration. So that's the problem. So now let's go into, so you might have a group where they're trying to say, will this startup, maybe they're making an investment, be successful? That's where we started, just saying, can you use collective intelligence to predict the future outcome of something that doesn't have a lot of data on it yet? It's an idea. And so many of our inventions are that way. They don't have history because they're new. And that's what we want. We want this idea of being able to support novel, new ideas that are frequently something that comes out of the human imagination. And so that's what we want to understand, how that core question operates. And so what we're going to say is that belief operates just like a field in the same way that uh, magnetism works. And this isn't just an analogy. What we're going to show here is that it's actually an isomorphism in the same way that the Hopfield model can be used to uh, learn pixels so that you can say dog versus cat or whatever other thing that you can learn, or you can say what sentence structures map to what sentence structures. This enables us to map what patterns of belief produce what sort of outcomes. So let's say you have people in a room, they're talking about, they listen to a startup, and here I'm going to say five just because I don't want to put 25 dots on a screen, but this actually works for at scale. Each person has an opinion. Think of that opinion as a belief with a vector. I think the team is going to knock it out of the park. Others may think, no, I don't think so at all. I think they're missing something. Those are each beliefs with a vector, an intentional direction towards the outcome. Um, Now, those beliefs, what we will say when people deliberate, the beliefs can influence each other. And we can look at that pattern of influence and interaction. So the key idea here is then we can say agents, meaning people, and I'm going to constantly use agent as a human, or it could be an AI agent. So far, the AI agents are very, very, very narrow in their capabilities, but nonetheless, this still works. And so we can say the structure of a group can be represented as a graph, as a connected graph. And that's really the starting point. Now, here the problem is that when five people, it's manageable to listen to everybody. 25 people, this shows you the complexity. There are uh, 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 300 lines of communication that have to be managed. It's suddenly, even at 25 people, no human being could actually listen to everyone and get each person to be listening to the other person in depth. And that's a big problem. So when you think about scientific discovery, people read papers, they think deeply about what the other person has said. So the big unsolved problem is how do we deliberate at scale? How can we listen to each other and build on each other's ideas at scale? This is what is known in computer science as an NP-hard problem. It does not have a solution. And this is why we typically break into groups. It was called the Mythical Man Month. And there are all kinds of forms that are used for this. This is why we use surveys and polling and various research techniques because we simply can't allow emergent understanding to be captured and elevated until now. That's what the belief field theory solves that problem. And it does it by using probabilistic learning over that network. And it kind of does a bridge structured solution that it starts to break the problem into sampling nearest neighbor interactions, much like you look at that group of starlings. What if you could sample what are the interactions that are going on, and then you'd be able to predict what those patterns may produce. Now, what I'm going to show you here is the method we're going to come up with is along the bottom green line. The red line is how complexity grows with the size of a group. The green line is what can happen with the process that we're going to be discussing here. In other words, it changes the problem from order of n squared to order of n log n, which is, I don't want to get into math on that, but just think of it as it doesn't get, it grows, its complexity grows at a much more manageable rate, meaning this can scale to groups of very, very large sizes. It's not, I mean, there's still a bunch of interactions, but it just reduces that complexity to a tractable problem, one that can be predicted. Now, uh, let's now begin to go into how do we do this? Well, we can, what is a field? A field is, you're all familiar with a temperature field. Anywhere in the space, there's a number, that's a scalar field. And the wind is a vector field. And so what we can, because it has a belief, and that's all we need to know for beliefs is the belief is, think of it as just a concept, a hypothesis, an idea that can be captured, an opinion, and it has a direction towards an outcome. Uh, and so we now have all we need to be able to say, instead of having a spin sitting in an atom, we have an agent with a belief. And then we have a field of beliefs, which is that complete collection. Now, here's what is true. It turns out when two electron spins are close to each other, they want to either be aligned or anti-aligned. It turns out that if you look at a murmuration of starlings, same mathematics as there's an attempt to line up. It's called exchange energy. This idea that there's a propensity or an attractor to be aligned is exchange energy. It is a real energy in physics that appears to happen throughout nature. There is a tendency when we're with another human being to want to be aligned. This is how we create social connections. So that is the exchange energy. There is no analogy here. This is just simply saying there is an energy that can be measured, and that is true. So what we now find is that when a group is aligned, the system energy is lower. And you can understand this again conceptually. When you're in a group where we all agree, there's less free energy, there's less friction. But what we'll find out is misalignment is our friend. It can generate structured disagreement, but that structured disagreement, the problem, can turn into a phase transition to a new idea. So this system, it shows us that when we get into these points of friction, we have a tendency to work our way out of it. This describes how humans are so resilient, come into a problem, we figure out a way. And I frankly believe that is never going to come out of the data and algorithms. Our problems are way too complex for that now. We cannot expect the all of the data of our history to somehow magically uh, be the oracle for our future. And so while I believe that there's tremendous power in generative AI, it is a stepping stone. And generative collective intelligence is that next step. So collective reasoning becomes a dynamical system. Deliberation becomes a dynamical system that you can only understand by looking at the interactions, not at the passive data, the data the agents left behind, which is what we do now, but of the dynamic real-time data of people working together to solve a problem. Now, my interest in this goes way, way, way back. I did a PhD thesis on understanding magnetic behavior in thin films. And this is snippets from a paper I published in 1971, 72. And it was about a mechanism that said fluctuations. You had the exchange energy where just what Hopfield did. But I was looking at on a real material where there's polycrystalline, it's many crystals, their structure, the things are all pointing different directions in places. That creates a notion of something, it's measurable. You can see it on a scanning electron microscope. Creates fluctuations called magnetization ripple. Some call it the Concordia effect because it looks like it's periodic. Um, and that structure results in a change in the dynamic properties. In fact, what I was able to show way back then is it can lead to regions of instability. It can lead to regions where suddenly, instead of relaxation happening, it can have a phase transition where it kind of amplifies, goes out of control. In fact, this indicated back then that you could use magnetic thin films as a parametric amplifier. Now, it turns out that I did a phenomenological model of this at the time that it was 30 years later that the actual magnon-magnon mechanism that was discovered to say that was true. For 3 decades, I thought I had published something that was not true, and it has now been later validated. And so what was always in my mind, what about if the Hupfield model worked for kind of belief alignment, which we've already shown in our experiments, what about the variability, the ripples in our beliefs? Can we understand that? Well, ripples in our beliefs really happens to deal with something that Scott Page discovered a decade or so ago, which is the diversity prediction theorem. That cognitive diversity is that belief ripple, right? And that is interesting belief ripple because it says if you have a group of subject matter experts, their ripples actually lead to greater predictive accuracy. And that's what we're going to look at. In fact, we can now say, we can now say this, the field is a field of beliefs, and then we have interactions between those that we discover by a process of peer review. So the way we learn of interactions, I say simply, I sample an idea from somebody else and say, do you agree with this or not? And simply we start to collect that areas of belief alignment. That's basically how the system works. And we can write a Hamiltonian for this, which is uh, the exchange energy is the interaction of attraction of two beliefs. The second term in that Hamiltonian is what happens if there's an external force field, a magnetic field, that's attempting to line that. By the way, you've all experienced that if you take a nail, an iron nail, old-fashioned iron nail, and you put it on a magnet, it normally its magnetic domains are all scattered about, but you put it on a magnet, they all get aligned and it becomes the magnet. So what that says here, that an external field in this case could be something that's evidence as pushing our beliefs in a certain direction. And then that third term is what represents cognitive diversity. It is the exact mapping to the structural diversity in a magnetic thin film. This is the diversity of cognitive training, backgrounds, etc. We're not saying here random. We're basically saying we're looking at maybe a diversity among subject matter experts or things of that sort. It could be random, but this could apply to a general populace. But nonetheless, just experimentally studying this, it's easier to kind of lock down the expertise a little bit. Anyway, it's Hamiltonian then encompasses the desire to be attracted to each other in beliefs and the fact that we have diversity. Okay, now we can look at the dynamics. When you wiggle one, like you saw in that thing from MIT, you wiggle one, it wiggles the whole group. So we can look at that wiggle factor in terms of an equation. That term on the right is noise. There's always some level of noise. The way we typically think about uh, noise or heat in physics is through a temperature. And what we will, and you see this in language models too. You can up the temperature of the model, and if you make it too high, it starts to be gibberish. It starts to generate gibberish. So we have the idea of the temperature. So any belief network has an internal temperature. And this is the intrinsic temperature of the belief field. Um, every field has a intrinsic temperature. This, in the universe, we've talked about the background radiation. That's an example of an intrinsic temperature of the universe. Okay, now we have two kinds of field, the belief field and the interaction field. The belief field is what each agent believes. The interaction field is the perturbations that happen when we peer review each other's ideas. We can measure that with citation weights. It's directly measurable, been used in scientific publications for ever since the Enlightenment. And this is also is what inspired Larry Page to do the PageRank algorithm that comes out of citation behavior. And that's what led to the Google search engine. So what we're doing is taking that and applying it now to how my wiggle in beliefs affects your wiggle in beliefs. The interaction graph um, is written by the deliberation itself. When we interact, we generate a belief manifold. So when the belief field touches the interaction field, we're now generating new things. And this turns out to map into a notion of collective belief excitations that are directly equivalent to magnetic excitation. So we're going to call this a cogiton. I'm not know if that's a good term or not, equivalent to a magnon. A magnon is a spin wave. You saw it on the MIT video where you poke it a little bit, it propagates through the spins. You poke a belief, it propagates through. Rumor, right? Uh, that is false belief, perhaps, that'll propagate. So we know this makes sense analogically. So we can go down through this very, very rigorously, and there's a mathematical paper to support all this discussion. The purpose of this presentation is to make the math a little bit more directly understandable. So The important thing here is that when groups interact, we are building a new belief manifold that does not exist in passive data. This does not exist in passive data. And so you're not going to get that out of generative AI. You're only going to get it out of generative collective intelligence. Now, uh, we have over the years, and I've been working on these types of algorithms since the mid late 90s, that actually came out. I mean, this is for if there are any business people who are watching this, is the way this started as I was CEO of Connect. And really, we were trying to work hard, getting ready to go public. I had a very strong management team. And when you have a very strong and diverse, cognitively diverse management team, getting alignment is not easy. And I had a consultant come in, and he had a methodology on index cards, which basically was this methodology of belief that we actually ended up putting into an algorithm and developed that over the years. So the core idea of this was to learn how can management teams be more agile in their decision making and focus and alignment. So I just want to say this is not pure physics theory here. Turns out that the two have a lot of similarities. So what we learned is that you want to start off with, and this is now something that evolved over, like I said, 3, 4 decades. You want to look at what, and this, by the way, you've been through this anytime you've been into a brainstorming session. The right-hand side is about divergent, right? The first thing you start off with is get all your ideas out. Get all your ideas out. Put the yellow stickies up on the board, as many as you can. That's the divergent term. And it turns out that what I'm going to use some very, very things out of quantum field theory, which is, and this, by the way, applies even on a stochastic network classically, basically it's the beta sampler functions as a gauge mechanism, a gauge field mechanism. And the beta field learner operates on a gauge field. And that literally means in quantum electrodynamics is this is how uh, we understand the formation of matter, the formation of mass from the field. And that's what we're going to look at here is the formation of beliefs that are adopted that matter to the group. That literally was coming out of this. So we start off with divergent. And then as we get all the ideas out, what happens? We start to move the group towards convergent. We want to know and exploit. What's the takeaway? What's the takeaway? What's the takeaway? And so that's what this algorithm does. It moves from high temperature, think of that, where we're a lot of information to focus. Um, and this turns out, we will show, this is actually a non-invasive way to measure what is going on with the group. Okay. Now, what makes this a gauge theory? I'm not going to go into the details on this, but it satisfies the constraints on that. And which is there's local symmetry. That means that any of us, any agent is free to believe what they want. You can rotate your beliefs any way you want. Nobody can get inside your head. They can, but you have the ability of agency to rotate your beliefs any way you want. There is parallel transfer. If I have a nearest neighbor interaction with someone else over a belief, that creates a transport mechanism, can either create alignment or disalignment. Now, here's the other thing. Have you ever played a game of um, telephone, right? I pass the belief to somebody else, to somebody else, to somebody else. When it comes back to me, it's not the same. That's called curvature. Now, what that means in a gauge field, that creates an issue. It creates tension. It creates frustration. Now, it creates novelty when it's a party game, but it creates frustration when you're talking with a group of people and they're operating out of a different frame of reference. That's what curvature measures, is the fact that all of us we don't have aligned ontologies. We don't, our state of being is different. And so we're always going to have some level of curvature. Curvature creates frustration. So if we do have complete alignment, a flat connection, this is usually with a hyper-aligned group, um, a strictly aligned group. And typically, Uh, that's often what is wanted by a tyrant or something like that, is to keep, not to have a flat. Uh, Curve introduces the opportunity for instability, and it introduces the opportunity for a phase transition. And this turns out to always, and this is think of it as the dialectic, the synthesis, I mean, thesis, antithesis results in a synthesis. That's kind of a curvature thing where we're doing a shift into something, a new state of being. And that's what this predicts. Okay, now that's cool. Now, what's the difference between aggregation and discovery then? Well, when you have a committee meeting, you're trying to assemble all the information. When you have a brainstorming session or a research group, you're in engaged dynamics. You're trying to discover the points of discontinuity and see if you can invent some serendipitous thing that breaks you out of it. So the gauge mechanism is a mechanism for serendipity. It is a mechanism for serendipity. This turns out, I think, to be extremely fundamental, that we can now look at modes of disagreement. The geometry of descent is a real thing. We can mathematically model in terms of eigenmodes, and these are the characteristic modes of operation. Um, the ground state, n equals 0, is where everything's uniform. And that happens in a magnet where it's perfectly aligned. A single crystal, whatever, perfectly aligned. It's almost an idealism, but that's the full 100% consensus. Um, the Anytime there is a potential disagreement, that results in partitioning of the group. It forms regions. In a magnet, that's magnetic domains. In a social group, we have it all the time. We have what we call bubbles, or things, groups that are formed that are aligned within the group, but then there's a boundary that they're not aligned. And so the productive zone is where we're finding ways of breaking through those boundaries to serendipitous discoveries of new paths forward. So we can actually predict this. We can now look at how fast belief wave fades. And we can also characterize resistance to change as a viscosity in the belief network, belief stickiness. So stubbornness, right, is simply a friction parameter. And it may be the variety of reasons that beliefs don't change. Cohesion is one. If I adopt a certain belief, it may affect my nearest neighbors, my friends, and therefore I may be resistant to accept that belief. That may be my reason for friction. This is all can be reduced to math. It's a Gamma 1 is just simply a predictor of the damping rate, and it can be small, larger, and it can have slow decay or fast decay. That's just the wave propagation through the belief field. So we can now look at curvature, frustration, and cognitive diversity. Uh, that cognitive diversity is a tensor. That basically, we're not just looking if with Page's diversity prediction theorem, he looks at it algebraically. That is, there's simple number. The variance in scoring is an indicator that correlates to the reduction of group error. Here, we're saying it is very complex. We can now model it in terms of many dimensions. Like here, you can say, hey, this is a person with a cognitive framing of a marketing person or an engineering person or whatever you want to map that out. So that now we have a way of mapping uh, the curvature disorder that is created by diversity. And then we can also look at how we manage that in terms of the friction. So this thing gives us a way to begin to look at how this impacts generative collective intelligence. So optimally, that we have a well-connected group with moderate diversity, but not chaotic, meaning you're not bring, but you want productive friction, not violent friction. And um, and then you want it that's sort of the ideal environment for group deliberation. Now, the one other thing, and this is a little bit of an aside, but because the space is curved, it doesn't make any sense anymore to use cosine similarity. And this is what's typically used in any AI model to say semantic similarity or two vectors. It just looks at purely, cosine similarity is purely a mathematical comparison of two vectors. It doesn't consider the information content of those vectors. The Fisher-Rao inner product, it considers the topology of a belief manifold. It's a surface, and think of it as murmuration of starlings. It's a complicated surface, and the curvature of that space makes big difference in terms of the distance. And so what we want to, we use this metric to determine the informational distance between ideas, not just the mathematical difference, but the semantic informational difference between ideas. So it's like a GPS, by the way. And if the GPS didn't take into account the general relativity properties of the curvature of space, you would be driving your car off the road. So that's the practical element of that. Now, there's a key discovery. I've been running a lot of experiments on this. I mean, literally 1,000 or more. And one of the things I wanted to determine is, does the instrument affect the temperature of the network? That is, does the beta sampler mess with the results? Is it a non-invasive instrument or not? And here's what we determined. It is not, it is a non-invasive instrument. There is a constant internal temperature to the network. In kind of the same way there's a sort of a lowest temperature in the universe, the what we call the microwave frequency of 3 degrees. Uh, this is the same idea in a belief field. There's a minimum temperature. Now, I am conjecturing that that is a indicator of quantum behavior. That I'll show you at the end of this what we have to prove for that to be true. But I think at this point it's a conjecture. So the effective temperature, TEFF, is really what the beta sampler does. Initially, I thought it was like a heat bath. Like when you go to the exploratorium and you see, the magnet, you can heat it up and it loses its magnetism and you bring it down and it sets back in again. I thought that's what a facilitator did to a group. They heat them up and let them cool back down again. And the question is, did it change the group? The answer is no. Uh, and I think that happens with facilitators as well. And again, I'm out on the limb here a little bit, but you ever notice the fact that no matter how good the offsite is, the group relaxes back to old behaviors within about 3 or 4 days. And that's the sense that the internal temperature of the belief structure is only momentarily impacted by the measurement instrument, and then it relaxes back. And that's in essence what we found with the beta sampler. It will raise the temperature in the beginning to get ideas out, but what it measures is very close to the true value of what people believe in the end. Now, and think of the internal temperature as the reasoning noise over belief friction. So, if you have a very noisy environment and low belief friction, you're going to have high temperature uh, to that network. If you have a high level of resistance to belief change and a low level of noise, it's going to be cold. It's going to be a very cold temperature. And by the way, that is it's so many of these things fit with our intuition. I get a little bit, but it's essentially there's like a 3% resolution limit on the, and we're still exploring what that actually means. So think of the beta sampler as a measurement apparatus. It measures, it prepares and measures, it prepares and observes. It does not change the result. And the component of the divergent component raises the temperature, the convergent component lowers the temperature, and but what it's measuring is the state of the belief network. Now, disagreement is our friend. And the reason it is because when we are in places of disagreement, there's curvature. That curvature opens up opportunities for serendipitous discovery. And this happens when, like, you have two different partition groups, there'll be a bridge that's formed between the groups that has the potential of bringing the two groups together. And you can only watch this in a simulator where and you can use, by the way, AI agents or human facilitators to help build these bridges. I mean, these are connections between red and blue or whatever, two different groups, not in my neighborhood, yes, in my neighborhood. There might be a connection bridge that then brings the group together. That is what, and in magnetism, there's something that is equivalent to that. It's called an angular kill switch, but that's what bridge formation does. It sort of moves the system into a phase transition, a new energy state. Um, I already covered that. Now, so what we've confirmed so far is, and we're still doing a lot of experiments on this. It is non-invasive. Uh, the uh, the sigma kappa convergence gradient seems to work, and so that seems to be validated. I've literally run hundreds of thousands of samples on this, and we're still looking at some other properties out of this. Now, I'm using AI agents to do the experiment, so this may radically change when we bring in humans. Right now, what we've determined is that if you're using agents from the same foundational model, no matter how much prompt engineering you do, they are not cognitively diverse. So I would uh, stand on that. I think that I haven't written a paper on this at all, but this, I think it's fundamentally calls into question this use of synthetic data if it's being generated out of the same underlying foundational model, just doing prompt engineering. Now, where you do get cognitive diversity is if you generate agents out of three or four different models like OpenAI and Anthropic and Gemini, and you take that approach. That does produce divergence and measurable cognitive diversity. The other thing, the background of this is keep in mind that in 2016 and 2020, we applied this to collective intelligence, prediction of investments, and there's a paper published on that. It was highly indicative that this was going to work. And so that was the inspiration for what we're doing right now. Now, underpinning all this is a notion of not just treating the field of vectors as a field of mathematical vectors, but mapping it into a semantic Hilbert space. And there's a formal paper on that that really pushes that. But what this says, if we can prove this and hold to that, is the belief field theory now has the properties of a Hilbert space, and this introduces an entirely new way to look at this in terms of the information metric as well. So this is really fundamental that we don't just treat the vector space as, set of mathematical vectors, but they really are a Hilbert space, which represents the state of the system. So if we were to take this into the quantum world, um, we would have to show uh, some things that this effective low temperature is a sense of the equivalent of a Planck constant for belief fields. Uh, I think that's probably true. It just means that there will always be a fluctuation possibility that creates serendipity. There will always be belief fluctuations that can result in some spontaneous creation of an idea. Makes sense. You have to prove it. Second, uh, this also predicts an uncertainty relationship, which simply says you can't know the state of belief of a group of agents and their learning rate with the same level of precision. It resolves to the equivalent of H effective over 2, uh, similar to the Heisenberg uncertainty principle applied to position and momentum. So position being knowing the state of belief accurately of a group, uh, but allowing learning. If you have any learning rate, you can't, if you know the learning rate, you can know that in detail, but that means the state is in, you have a limit on the prediction on that. They go back and forth. Again, that makes sense, right? That you don't, if a group is forever thinking and changing, there's going to be a minimum amount of precision you can get out of that. Now, if we do prove uh, the that is quantum, then we can start to look for some additional behaviors that are purely quantum. One is tunneling. There can be tunneling between consensus opinions. This can be jumps. This would mean that a group in a different part of the world is coming to the same discovery at the same, in some similar time frame. So that would be like a tunneling effect. There could also be uh, uh, just an irreducible floor for serendipity, that it could always happen. That is the same as the quantum fluctuations in a vacuum. And a big one is entanglement. Again, this sort of makes sense, but it says if two agents have interacted, then they are forever entangled in some way. And so a state change in one may indicate a state change in the other. So those are some possible things that could come out of this. So we know some things so far, and it's very promising, but there's a lot of work yet to be done. Particularly, this has all been done so far just with agents, not with human agents. And that's going to be a lot more complicated to do those experiments as controlled experiments. And also the early case that we did using collective intelligence for investments does not qualify as deep scientific research. It was practical data collection from an actual operating investment activity. So we did not have the ability to do the controls, et cetera. So what this calls for is really doing some, very, very disciplined work around the experimental side to determine some of these capabilities. So what does this framework mean? Well, it means this could have a big impact on how we design things, how we design our planning and future, how we do decision making. It has a huge impact on potentially how we uh, synthesize knowledge within science. I mean, one of the problems we have right now is millions of papers without the synthetic ability to kind of how do we integrate it together. It also has implications on agentic AI, how we can actually bring multiple models together for have them learn better together. I'm going to take a little bit of the application into field intelligence, and this is based on work by Indy Johar and Dark Matter Labs. Um, and this creates more of how you take this into an actual design experience with social and corporate transformation. So uh, you can now begin to look at a bridge formation mechanism where you do exploratory links and trajectory spanning a convergent reinforcement and topology chains. All of this now you can see fits into the framework that I laid down for belief field theory. You can also look at how fragmentation then looking for these bridging techniques can lead to degeneracy breaks and formation of new pathways forward. Uh, which, by the way, this is independent work that Indy did in defining this, and I'm simply bringing this together into how a belief field supports um, this capability. We have an ability for doing distributed sensing uh, and essentially do distributed truth finding, epistemic sovereignty, uh, and really looking at provenance and representation, which I think is a fundamental problem in these areas. So we have the ability now to begin to develop an actual system for metacognition and operationalizing it in how groups work together. We actually now can create visual models that will support this process. And I won't go into these things in detail, but these are actually things that we can now instrument, measure, and project back to the group. So I think there's a lot we can do with graphical models here that enable people to see their collective thinking together as it evolves. There are ways here now to um, actually begin to look at how this impacts governance and economics and uh, legal structure, et cetera, things of that sort. Uh, that is apparently something that we can now begin to approach using a field model as opposed to, and because field model basically brings us in this, the part and whole relationship becomes extremely important. So here we have a potential field intelligence architecture that can be built on top of this belief field idea. And so intelligence is just an emergent property of the field. It's not the output of any single agent. It's just simply an emergent property of the field. I frankly think this is uh, a way we ought to be thinking about AI going forward as a field. And so we're not hung on the particular lens we use on navigating that field, but we build the right field. We build the right embedding structures. We use transformers to build, because all of this is dependent on the quality of the embedding structure, how we lay out the semantic Hilbert space. But if we do it right, I think we can get fantastic leverage out of it. So this leads to potential for breakthrough capacity. We can have structured dissonance without collapse. Uh, we can have bridge-enabled discovery. We can have fast error correction. And we can now think about even how this leads to an entirely different kind of economy, more of a knowledge economy. And there's a lot of ideas that can come out of that. So going back to what we said before, this framework now can take that application, the potential, and map it into actual um, structural implementations within organizations. This is just a glossary of terms. I'll make this deck available, but this is basically the idea. I'd love to have thoughts, feedback. This is work in progress. Very exciting. I think there's a tremendous potential in what we can do with this. Thank you very much.